Hello and welcome to this presentation of Semantic Concept Annotation for Tabular Data. This is work published at ACM-CIKM in 2021. In this work, we are dealing with column to concept annotation, where you're basically provided with a table full of values in rows and columns, but without column names or concepts. And the job of the annotator is to figure out appropriate concepts or column names that befit all the columns in the given table. This actually helps in a lot of applications, starting with better readability to machine learning and several downstream tasks. However, this is a complex task which involves several challenges, starting from multiple interpretations of entities to the fact that many of the current approaches mostly rely on knowledge graphs, which are limited in coverage and may not be able to provide a wide variety of concepts for real web tables or real tables present in corporations. They also have challenges with numeric columns because of lack of numeric data in knowledge graph. Prior work is mostly based on supervised learning based methods, which requires a lot of gold standard data, and hence these methods are difficult to scale. On the other hand, we provide C square, which is a novel system for column to concept annotation. And our key difference with respect to previous techniques is that we utilize millions of openly available tables on the web. In this case, at the time of this paper, we use 32 million tables. The advantage with such tables is that they provide a much wider coverage of concepts and entities. However, these are noisy, these might be incorrect and incomplete. And the important, interesting things in the paper are basically about how to utilize this noisy and partially incorrect data to effectively outperform methods that are based on supervised learning using gold standard data. So in our the technique we present here, we present a maximum likelihood estimation based method, and it provides a probabilistic ranking of concepts that best explains the presence of all values in a column. Um, this is an illustration which conveys the basic idea, wherein for each entity in a column, we look up what column names have been associated with it in the past in these millions of tables, and we try to find concepts that are most widely applicable throughout these entities. So this is a simplistic example in which we do not provide counts and probabilities or the variety of sources that we source the data from. However, it illustrates the spirit that if a concept is present all across for all the entities, it might not be the first choice for any entity, but it still can be the answer if it explains all the entities present in the column. In a slightly more uh, realistic scenario, still illustrated though, we highlight that for given a given column, using different sources of data, we find different counts for each column, each entity concept pair, and for each such concept that is found for that column, we compute a maximum log likelihood estimation, where we also use smoothing to make sure that we don't miss out on certain concepts if they were not absent, if they were absent just like once or twice. The In the interest of time, I'll skip a lot of the details, but this is the general architecture of C squared. where on the top layer you see data, which is either knowledge graphs or data lakes. We use both, and there's no limitation in the sense of using only 32 million tables. And since then, we have actually been using more, and you can just add any new different data source, and usually it gets the performance becomes better. In the middle layer, you see several indexes, one of which I just showed you through a simplified illustration. But there are several different indexes which help perform this log likelihood estimation method. And these are at the bottom, you can see those estimators which perform those estimations. So one of the examples of another such index is the tuple validation index, where uh, in the given case, you can see that there are two columns, one which everybody will see and say that these are movies, and the second column looks like the could potentially be like year and possibly the year in which the movie was released. But there's also this possibility that these are those novels, because all these movies are based off of novels, and but novels are usually less talked about than movies. So you'll find those instances in fewer tables. So one can guess that the top result would be a movie or a film, but book is like a second ranked result in this case. However, if you carefully see, the Godfather movie did not come out until 1971. It was, in fact, the novel that came out in 1969. So one could argue that by actually closely looking at these pairs of values, that uh, the first column actually refers to the book, and the second column refers to the year of publication. And this kind of re-ranking happens through an index that we specifically constructed here, and the process is called tuple validation. So there are several such indexes which have different roles to play in terms of likelihood estimation and re-ranking and so on. So in the interest of time, I'll not go through each index, but I'll refer the interested listener to our paper to go through all the relevant indexes. And we also perform things like belief sharing, which is like, because we don't follow a closed dictionary, one could get a movie and a film as different results. So at the end, there's some sort of conciliation where we say that okay, movie and film are the same, or in another case, professor is a kind of human. So all professors are human beings. So if there's a case where 40% of the results lead to professor, 60% lead to human being, we can say okay, actually 100% of them are human being and 40% of them are also professors. So one can find several system details in the paper, but I'll briefly talk about comparison to then state-of-the-art systems such as Sherlock, Sado, and CallNet. And we used 8 different openly available benchmarks from some of these papers, and some of them were from the SEPTAP challenge, and one of them was actually created by us, which is also available online. All of these data sets are available online, and we do pretty well against all three: Sherlock, Sato, as well as Callnet, and we're happy to compare against any other recent techniques, whichever is open source. So thanks for listening, and if you have any questions, please reach out.